The next topic that we're going to talk about in trying to match shapes or any other templates on an image is the method known as Hough transform. Once again, this lecture's slides are also based on the excellent lectures of Professor Yani at India Ren, as well as the lectures of Professor Mubarak Shah at the University of Central Florida. We've already seen a couple of line fitting methods. We saw least squares fit, and then we saw ransack. The question that we're going to ask now is, what do you do if there are multiple lines placed in a particular orientation or placed in a particular configuration in an image? It could be multiple lines, it could be a polygon, it could be a circle. Then how do you deal with fitting a shape onto the set of data points that you have? And that's what we're going to talk about now when we go to Hough transform. This method dates back to the early 60s by Hough, who filed a US patent for this. But since then, there have been many efforts that have translated this into what we see today. In the early 70s, the Hough transform was used for detecting of lines and curves. Then in the early 80s, there was a method that came that was called generalized Hough transform, and we'll see all of these over the next few slides. Let's start with the simple equation of a line in Cartesian coordinates, which we all know is y is equal to mx plus c, where we say that m is the slope and c is the y-intercept. You could just play with the terms in the equation a little bit and then write this as c is equal to minus x into m plus y. Rather, we now live in an MC space where x and a c intercept y define the line in that space. So we were originally in the xy space where m defined the slope and c defined the y-intercept. We could just rearrange these terms slightly to now go to an MC space where minus x becomes the slope and y becomes the c-intercept. In this kind of a context, every point in m comma c in that space becomes the equation of a line in the xy space. Remember, for every choice of m and c, you will get the equation of a line as we see here. And every point in the xy space similarly would become the equation of a line in the MC space. There is a dual correspondence between these two spaces. So what do we do with this? We know that to fit any model, we need a certain number of samples. For example, to fit a line, we need 2 samples. If it was any other model, if you were fitting a square or a circle, we need a different number of points. To fit a line, you may need 2 points. Let's start with that example. But even if you had just 1 point instead of 2 points, you know that it could belong to a certain family of lines. It gives you some partial information about the line equation itself. So what we can ask every point in your xy space to do is to vote for certain configurations of m and c in case we're talking about a line. If a line, every point can vote for what configuration of m and c would have resulted in this point being at that particular location. And then you collect votes for all such points and then try to seek consensus. And wherever there's the majority vote, you're going to say that that is the equation of the line that I'm looking for. Let's elaborate on this and go through slowly. Before we go forward, we spoke about the Cartesian coordinates on the previous slide. Unfortunately, the Cartesian formulation can be problematic for vertical lines. Can you say why? When you have a vertical line, your slope is unbounded. it becomes difficult to represent such a line in your MC space because M has to be infinity. So in such a scenario, it may be wiser to use a slightly different parameterization, the polar parameterization, which is written in terms of rho and theta, where rho is the distance of the line from origin and theta is the angle made by the normal to the x-axis. You can also write rho as x cos theta plus y sin theta. This is a standard polar parameterization that's used going from Cartesian coordinates to polar coordinates. We know now that in this space, rho is bounded, at least lower bounded by 0, and theta lies between 0 and 360. We know that these quantities are bounded, which makes it slightly easier to work with. So every point in your original space, in your Cartesian space xy, votes for many points in your parameter space. So if you had a certain line, certain point x1 in your original Cartesian space, for the moment we are going to talk about this method generally in terms of a Cartesian space and fitting a line or fitting a circle and so on and so forth. A little later in this lecture, we'll talk about how do you use this with images. If you have already sensed what's coming, we are trying to find out how do you use Hough transform to match lines or circles or any other shape in an image. That's the goal of this lecture, of the method discussed in this lecture. But before we go to an image, we're just going to talk generally about Cartesian coordinates. So if you have a point x1 in the xy space, you know that there are a family of lines that can pass through x1. And each of those lines has a correspondent m comma c. It's going to have a slope and a y-intercept. And all of them will result to corresponding points in the MC space or the r theta space. If you go to the log polar space, you'll have a slightly different notation. They'll correspond to a point here in the r theta space. So for every point xy can vote for many points in your parameter space, which that particular x1 point could have been lying on. So each line through this point x1, y1 is a vote for a point in a parameter space which satisfies rho is equal to x1 cos theta plus y1 sin theta. Let's see a few examples. Here is another line that passes through x1 and that would vote for a different point in the parameter space, which is here. Here is another line that passes through x1 that would vote for a different point in the parameter space. Remember, the parameter space now is defined in a polar parameterization, and you keep repeating this for several lines that could have passed through x1 and all of them get votes in the parameter space. Similarly, you could have another point x2 in your original space through which you would have another set of lines that can pass in your original Cartesian space, and each of those lines may vote for a different parameterization in your parameter space. You can see that again here with several examples. For several lines that pass through x2, you get several votes in the parameter space. Let's try to recount this through an algorithm. So you have your data x, you have a set of quantized parameters theta min to theta max. For example, if you take your polar parameterization, you may not want to vote for every angle between 0 and 360. You may want to divide 0 to 360 into 10-degree bins and have only 36 possible theta values. That's what we mean by a quantized parameter here. You also initialize an accumulator array, which is simply a frequency count. It's simply a frequency count of votes. You can look at it that way. So for every point xy in your Cartesian space, we try to see for theta belonging to theta, you have 10 possible thetas. If you write out rho is equal to x cos theta plus y sin theta, we try to see for each set of model parameters consistent with the sample. So which rho and which theta would align with this particular xy that we have taken. You increment the A for that theta and rho. So imagine the accumulator being a 2D matrix defined by theta values on one axis and rho values on the other axis, which could also be quantized. You could quantize distance into distances of, say, a certain number of units. And whichever rho and theta we know corresponds to this x and y that we have, you go to that rho and theta, and in each of these cases you could check for consistency and increment that cell in the accumulator matrix by 1. And you keep doing this for every xy point that's given to you. Those are your set of points that are given to you. And you keep accumulating, and at the end, you do a non-maximum suppression in A. So if you have many different bins that have a high vote, you do a non-maximum local non-maximum suppression to see which bin has the really highest votes, and you define that theta and rho to be corresponding to the model that corresponds to your that directly has a bearing on the data in your X matrix. This gives you a way of estimating the theta and rho, or in Cartesian coordinates finding the equation of the line corresponding to this set of points that are given to you. Okay. This is, as you can see, this is very similar to a least square fit, but doing it in a slightly different way. We are still trying to fit a line to a set of points that's given to us, but we are doing it using the Hough voting approach. Okay, now as I promised, here is an example from an image perspective. Let's say we have an image, and the image has several lines, and we want to find the equations of those lines. Right? There could be several applications where this may be required. Let's say, for instance, that you're trying to take images of a computer chip and try to find out, say, how those lines are aligned on a computer chip, or so on and so forth. Right? You want to find the equations of those lines. So using the same approach that we just talked about on the earlier slide, you assume a certain parameterization. You ask for each point to vote to which parameterization may have generated in that particular point, and you end up getting votes over your accumulator 2D matrix, which is, say, rho and theta. So you can see here that you have a bunch of votes that spread across many different accumulator bins. We said that the accumulator is a matrix with rho and theta. Now you do a non-maximum suppression to maintain only the local minima in your accumulator. And once you do this local maxima, you find that there are 4 maxima here, which corresponds to 4 values or 4 parameterizations of lines, which are the 4 lines that you actually have in your original image. And those are the points that were voting for each of those accumulator bins. This way, you can find out the equations of those lines, as well as which points in the original image correspond to those equations, to be able to extract that shape in the image. So you can actually find equations of lines in any image given to you using this approach. Let's make this a bit harder now. Let's say we want to now find circles in an image. We did talk about blob detection earlier, but now we want to exactly find the circle with its radius and center and be able to parameterize it perfectly. So circle fitting is very similar to line fitting. Okay, that's going to be the fitting that you're looking for. X minus x naught square plus y minus y naught square plus r square is equal to 0. What should be the dimensions of the accumulator? For line, the accumulator was a 2D matrix. What would be the dimension of the accumulator for circle fitting? It would be a 3-dimensional accumulator where you have x naught, y naught, which corresponds to the center of the circle, and r, which corresponds to the radius of the circle. Those are the 3 votes that each point is going to be voting for. So the way, since we have three possibilities here, one option is to fix one of the parameters, and generally you fix the radius and then loop for the rest, ask every point to vote for just the center, and then you can keep going around and going in a round robin manner to ensure that every point votes for all 3 parameters at the end. So you keep incrementing the accumulator for every vote that a point makes to each of these values, and at the end you do a local maxima in A, and this way you can actually estimate the parameterization of the circle that you're looking for. Here is a visual illustration where, given a set of coins in an image, you can actually now find out where those coins lie and what is the radius of that coin by first extracting edges. So in this, you have to first extract edges and then be able to use those edge information to be able to find the exact parameterizations of the circles. When I say parameterizations, I mean define the centers and radii of each of those circles that you have. You need not stop with just lines or circles. You can obviously do this for any other shape. As long as you can parameterize any shape in an analytical manner, you can give a set of equations to define a shape. All you have to do is take a point in your original image and ask it to vote for what would be the parameters of a polygon that point belongs to or lies on. And then you just count which parameterization got the highest votes amongst all the possibilities in your parameter space, and simply define that to be the polygon or any shape that you're looking for. But what if you're looking for a shape that has no analytical description? For example, on this slide, you see this irregular shape which has no analytical distribution, which has no analytical definition. How do you estimate, how do you find such shapes in an image? We do assume that the shape is given to us. So you do know that this is the shape that you're looking for in a given image, and it could be of different sizes, could be rotated in different ways, could be scaled. All of those transformations are possible. But we want to find where in the image it lies. The only thing we know is that this shape, in this particular case, may not have an analytical definition. You cannot write it as an equation. What do you do in this particular case? You define a reference point in the shape. Right? You could define, for example, an x0, y0 as a reference point in that shape. And now every edge point of this shape can be defined with respect to that reference point. So every point here, say xy, has a certain length from your reference point x0, y0, and a certain angle with respect to the reference point x0, y0. As an example, x0, y0 could be the centroid of that object that you're looking for, but it need not be the centroid, it could be any reference point. So once you have a centroid or any other reference point, for each edge point that you have, so remember again that given a new image, you have to first do an edge detection to get the edge points. Then for each edge point, you compute what is the distance to the centroid. You would first do this for the template object that you have before you run it on any new image. This is when you know that this is the shape you're looking for. You define a reference point. For each edge point in this particular shape, you compute a distance to the centroid, which is Ri, and an edge orientation phi I. And then you create something called an R table. And what the R table says is that for a given edge orientation phi 1, what are all the possibilities? What are all the points that could have a certain radii with the same orientation with respect to the reference point? Similarly, for another point with another orientation phi 2, let's say phi 2 is this particular edge point, that has a certain radius with respect to the reference point. Similarly, there could be another point with the same angle which would have a certain radius R21. There could be a third point with the same angle, same edge orientation, and that could have a radius R23. And you create an R table which connects these orientations and these distances to the centroid or the reference point. So once you've built this R table, what do we do? Here is the algorithm of what is known as generalized Hough transform. So you have your data, you are given your R table, which you've already built from the shape that was given to you. Remember once again that the shape is defined for you, right? Not defined, is given to you. It's not well defined mathematically, is given to you. Using that shape, you construct something called the R table, and you also construct an accumulator array for how many ever dimensions you have to estimate. So if that reference point has 2 coordinates, you have only 2 coordinates to vote for. Otherwise, you may have other parameters too. If you allow your shape to change in multiple ways, you could have other dimensions in your accumulator for which also the points can vote. In this particular case, to keep it simple, let's assume that the shape is going to be the same, just that the shape could be placed anywhere in the image. No scaling, no rotation. Let's assume that that's the scenario here. So the only thing that we are trying to find is where would the centroid of that object be. So you have an accumulator array which is of two dimensions going from x c min to x c max. C min and c max are the maximum values of that the centroid can assume in the x-axis. Similarly, y c min to y c max. And you initialize the accumulator, every cell of the accumulator to 0. Then for every point, for every ri phi I in your R table, you try to write if your centroid can be written as this x plus ri cos phi plus this y plus ri cos phi. If you can write your centroid with respect to this given xy using this particular formula, you would increase the accumulator for that particular centroid. And you would keep doing this for various different centroid possibilities, where your centroid possibilities will come from xc min to xc max and yc min to yc max, where you discretize your possibilities of the centroid and you create an accumulator array. That's the way you would do it. And at the end, you would get a set of values, a set of frequency counts as to what each xy voted for. And you do a non-maximum suppression to find the local maxima. And that's going to give you the final xc, yc, which correspond to this new set of points that are given to you. Speaking in terms of images, once again, let's assume that this is the shape that you're looking for. As I said, we assume in this example here that we are only looking for this shape as is. No scale change, no rotation change. So which means the only thing that can change is the center of the object could be on different parts. So that's why we're voting only for where the center is. And so given a new image, you run an edge detector, and for each edge point, let it vote for where the centroid would be. And wherever you get the maximum votes for the centroid is where your centroid is potentially could be. You could use this kind of an approach to say find a car in an image. If you knew a car has a particular shape, you define that shape, you now ask you run an edge detector on a new image and then ask each point on the edge to vote for where the center of the car is, and based on that you can probably trace where the car is located in the given image. So you could use such an approach even for object detection. Again, within certain changes in your shapes, in the possibilities of the shape. If a car's pose completely changes, obviously this kind of an approach will not work in that scenario. Okay, so it works only with certain tolerance. To summarize the Hough transform, it's an effective approach for detection of shapes, objects including say multiple, even if there are multiple cars, you can probably find all of them. You could have multiple maxima in where edges vote for the centroids of the cars, and each of them may be different instances of a car in a given image. So you can also use this for detection of multiple instances of object in an image. The advantages of the Hough transform is that it deals with occlusion fairly well because it's a voting procedure. If as long as the number of votes is high, it does not matter if certain votes went wrong. So even if a certain part of the object was occluded, it can work. Obviously, if a significant part of the object is occluded, it will not work. It's also robust to noise for the same reason, because you only need to look at a certain set of pixels, and as long as they vote for a majority, you're going to get your shape or object in the image. The problem here is it can be computationally expensive because of depending on how you quantize your parameter space. Remember that every point has to cast a vote for different possibilities in your parameter space, which can be time consuming. And setting your parameters and quantizing them may not be easy for different kinds of shapes. For line, circle, and a few well-defined shapes, it may be straightforward. For certain other shapes, this may not be easy, or quantizing them may not give very accurate answers. Those are some limitations to work with here. Here, is the visualization of the car example. So you have a model image and there are some key points with respect to a reference point at the center of the image. So you record the coordinates relative to the reference point in the model image, and for every test image you look for the same configuration of the key points with respect to the centroid of the object. So in these particular cases, the car is inverted, but when the test image is of the same configuration as the original object, you would find a match in this particular scenario. Here is one more example. So if you considered your model image to be the Eiffel Tower, and here is a test image, which is also the Eiffel Tower taken in a different scale on a different day with different lighting conditions. You then have your accumulator. After you find your model image points in your original image and your test image, you have your accumulator that votes for the centroid of the object with respect to various key points in that object. You consider a local maxima. You may not see it very clearly here, but the local maxima is somewhere in the middle. And based on that, you vote for where the Eiffel Tower is located in the test image. The homework for this lecture is chapter 4.3 of Selesky's book, and a couple of questions for you to think about. How would you use Hough transform to detect ellipses, squares, and rectangles? Try to work out what the parameterizations or the analytical forms of each of these shapes is, and try to find out how the accumulator array would look in each of these cases. That should help you address these problems. And a real world use case. Let's assume your friend working in a diagnostic startup asks you how to count the number of red blood cells in a blood sample automatically. So you have a blood sample, you want an automated way to count the number of red blood cells using Hough transform. What would you advise him or her? Something for you to think about. And here are the references.